As you might have guessed, I am a Python developer. And as a Python developer, I'm used to think high level. Maybe it's the case for you as well, maybe not. But, you know, for example, when you create a list in Python, you don't think about how it is represented in memory, right? Especially if you don't have a CS degree, or if Python was your first language that you ever learned. Take me, for example. I did not know what an hash map was. I did not know how a dictionary was implemented, how it worked, the magic behind it. That until I started learning Rust. You know, Rust is a lower level language, more like C and C++. And if you use that language, it's really hard not to think about the memory, not to think it high level, low level. So what I just learned tickled my curiosity, and I asked myself a fundamental question. Can we learn something useful by studying how Python is implemented, how data structures are implemented? This is the question that we'll try to answer today. And this is another question that we will try to answer today. I'll give you 5 seconds. I'm sorry, I'm going a bit fast because I have very little time. Wow, I'm shaking. Okay, let's start with a few concepts so we are all on the same page on everything. Let's start with the Python implementation. Now, the manual definition of a Python implementation, you can read it there. It's a program which provides support for the execution of programs written in Python. Okay, what does that mean? It's a piece of software that allows us to transform the human-readable code, the Python code, into machine code and execute it, right? The main one is CPython. It's written in C by Guido van Rossum, and it's the standard, the one that most people use. There's a few more. It's not the only one. Here you have a few examples. I like MicroPython because it allows you to write code in embedded systems on microcontrollers. Arduino, for example, I love that. And then there's Jython that allows you to run Python code on a Java virtual machine. I don't know if that's even legal. Next thing we're gonna see is compiled versus interpreted. You know, you can divide programming languages into 2 macro categories, compiled and interpreted. Compiled languages like C, Rust, C++, have this concept of compilation, which is transforming the human-readable code into machine code all at once before the execution and producing an executable file. Interpreted languages like JavaScript, PHP are a bit different because they compile each line one at a time during the execution. As you might notice, there's no Python in the example because Python is an hybrid language. First, it compiles into bytecode, which is an intermediary language, and then it interprets the bytecode. Why do I explain this? Because we need to understand a couple of words, which are compile time and runtime. They define the time of when something can happen. If something happens at compile time, it happens during compilation, so before the execution. And if something happens during runtime, it happens during the execution. Another way in which you can divide languages is statically typed and dynamically typed. Statically typed means that their types are defined at compile time, and the type cannot change over time. And dynamically typed means that the types of the language can change over time, like in Python, for example. Even though sometimes it might not seem, because in Python there's type hints, but they do not enforce types. But you can enforce them with type checkers, though. If you use type annotations and type checkers, the experience of programming in Python can be very similar to with statically typed language. Let's try to talk a bit about how types in Python work. we have to define a couple of words, 3 actually. Variables that contain, when you declare a variable, the value of the variable is not right inside the variable, it's somewhere else, and in the variable you find the reference, basically the address of the physical memory in which you have an object. So everything in Python is a reference, everything is also an object. Objects have 3 properties: value, identity, and type. The value, let me see, this is an example. Let's see, we have this variable solution equals 42. The value, of course, is 42. The identity is the address in memory. And there's this useful Python built-in function that allows you to see that. It's the address in the physical memory. It's the physical address in which you can find the value. And then the type, which is the class that it inherits from. This, I think, is a little proof that everything in Python is a reference. So you have first a variable, a equals 42, then you assign the variable to another variable. What happens there? You are copying the reference. Hence, the 2 identities are the same. A useful thing, no, I don't know if it's useful, thing to know is that Python pre-allocates small integers. So in this example, we have 2 variables with the same little integer value, which is 5. And you can notice that the identity is the same. This happens with integers from -5 to 256. This is something that the Python team decided because probably these integers are used a lot. Here's a little proof that if you go outside the range, that does not happen anymore. Let's talk about mutability and immutability. Objects in Python can be mutable or immutable. Mutable means that their value can change without changing the identity, without changing the position in the physical memory. Sorry, I said, no, correct. And immutable are the opposite. Here's a little example. Let's say that strings were mutable. They're not. Here's a little representation of the memory. On the left, you have the address of the memory. On the right, you have the value. When you change the value, it's changing in place in memory. And otherwise happens with the, with immutable types. As you can see, the object is destroyed and created somewhere else in the memory. The identity changes. Okay. Here's a few examples of immutable and mutable types. You might wonder why so many types are immutable in Python. You know, you have a variable, the value has to change. So why are they immutable? I don't know, but here's the answer that I gave myself. Okay, now here's a little example. With int, you can see that if you change the value, the identity changes as well. Why? Let's see this other example. You have a variable with a value, and you assign the variable to another variable. You change the second variable value, and the value of the first value, the value of the first variable is still the same, does not change. Remember that I told you that in Python, everything is a reference. So when you do the assignment here, you copy the reference. So what would have happened if int was mutable? This. Here you copy, here you copy the reference. So both variables point to the same object in memory. And if you change either of one, the value changes. This happens with lists, so be careful. Okay, let's talk about lists. How are they implemented? We're going to just scratch the surface. They're internally implemented as dynamic arrays. What does that mean? Array means that all the items in memory are stored contiguously, one next to each other. Here's a little example. And dynamic, it means that they can grow or shrink. They can get bigger or smaller. What would happen if we had another variable and its value would be right after our list, and then we wanted to append something to our list? The list has to grow, right? Here it cannot. What happens is that the list gets destroyed and created somewhere else. Here's another little example. While I was preparing this talk, I was not really satisfied with this explanation, so I decided to dig a bit deeper, and I went into Python source code. After a bit of searching, I found this object. I'm really not proficient in C, but I tried anyway, and then I found this method. So this file is where the list object is implemented in CPython, and in this method, there's some code that is called when you call append on a list. Here's what I found. I think that among you, there's someone that can read this line in 1 second and understand what it does. For the rest of you, don't panic. The rest of you and me. I will explain it a bit. I wanted to go a little bit deeper into the binary logic, but there's no time. So we have to jump a few slides. I will go directly to what that line means. Essentially, it chooses how a list has to be big when an append is called. What does it do? It overallocates. So it creates a bigger list, leaving some space at the end, in case that more appends are needed, are called. In this way, Python does not have to destroy and recreate the list every single time. It does that with this pattern that you can see there, 0, 4, 8, 16, blah, blah, blah. That's a bit weird. It can be explained if you look into the formula. I will just explain a bit what it means. This is a shift operation, right shift bitwise right shift of 3 operation that is essentially dividing by 8. It's binary logic. If you want to dig more into it, do that because it's amazing. I just don't have time to explain it. This is an AND, not 3 bitwise operation. It basically rounds down to multiples of 4. And it just does that in a very efficiently manner. That's why it's like Arabic or Chinese. 6 is a constant, so what the formula does is divides by 4, adds 6, adds new size again. New size is the size that the list would have after the append, and rounds down to a multiple of 4. So this pattern then is followed. If you do a lot of appends, the list follows that growth pattern. So which one is faster? Yes, of course, because it pre-allocates. It creates a list, an empty list, and it populates it. So the list never gets destroyed. In the first case, the list gets resized a lot of times, and that takes time and resources. What can we learn from these list things? Of course, what we just said, that pre-allocating is faster than appending. I mean, in Python, it's not always useful to do that in, how would you say, what you lose here maybe is readability for, I don't know, maybe junior engineers. So if you have to do that, maybe leave a comment and explain why you did that. Python does a mild overallocation, like 12.5%. Not sure what we can learn from this, to be honest. But what I thought about is this. What happens every time that your project manager asks you, what time will you take to do this task? You say, for example, 2 weeks, and then you take more than 2 weeks. So, like Python overallocates, we should overestimate our tasks, not just of 12.5%, but maybe 20, 50 even. I don't know. Okay, let's try to talk about sets and dictionaries. But first, we need to talk about hash functions a little bit. What are hash functions? They're functions, algorithms, that do something similar to this. This is just an example. They have a few characteristics. The first one is that the output has always the same length. Given the same input, it will produce always the same output. If very similar inputs are given, the results are greatly diverse. We'll see an example in a bit. What was the? I don't remember it by heart. Okay, it can happen that with greatly different inputs, the same output, you get the same output. This is called hash collisions. We'll talk about that in a bit. Okay, yeah, converting the hashed values into their original data is not possible. And also, their calculations are very fast and relatively simple. Okay. This is a little example with the SHA-2 algorithm. It's a very famous hash function. And here you have hello world with an exclamation mark. And you can see that if you just remove the last character, the output is completely different. Why do we talk about that? It's because we need to define what a hash table is, the magic behind dictionaries. Let's see how the theory works. So a hash table is a data structure that can contain pairs of keys and values. Okay. Let's say that we had a list with these values. We have names as keys and favorite colors as values. If you want to look what's Daniel's favorite color, we need to search into the list. Use a search algorithm or use a linear search, and it takes time. How do hash map works instead? Let's start with an empty table and inserting items. We want to insert John. John is the key, and it's passed to an hash function, which outputs that. Then we do a modulo operation of the hash with the size of the table to distribute the values better, and we get an index. Then we place the hash, the key, and the value in that index. And we do the same for every values. We have Kate in position 2, Charlie in position 0, Desmond in position 3. Then we have Daniel. And the result of the operation is 3. But as you may notice, position 3 is already occupied. This is something similar to a hash collision. And in this case, the theory says that the item is moved into a list in which there's going to be both Desmond and Daniel. So if you then try to do a lookup, we want to know what's John's favorite color. We hash it, we do the modulo operation, and we have the index of the place in the table. So we can access it directly. It's way faster than doing a search. Well, with a lookup, if we want to do a lookup on Desmond, we land on row number 3. We see that there's a reference to a list. We go into the list and we do a linear search. But the linear search is performed on a list that is ideally much more smaller than the original hash table. Now, that was the theory. How do they work in Python? It's a bit different. It's a bit more complicated. But first of all, when you declare a dictionary, Python pre-allocates an hash table of 8 slots, 8 indexes. And as you may read, it pre-allocates a table of indexes. So you have an hash table, yes, but it does not contain values directly. It contains indexes. So you want to insert a value, joy in this case. The result is of the modulo operation, or taking the last 3 bits, is the same, is 1. What you insert in the table is 0. 0 is because this is the first value we insert in our hash table, in our dictionary, actually. And then we have another table in which, at position 0, this one, we have our object, or the reference to our object. Actually, we have the reference to our object. Lists are lists of references. What does this mean? I spoiled that dictionaries are ordered. Is someone still using ordered dict? By the way, this is valid from Python 3.7. Before, there was just one hash map, like normal one. Just mentioning that when hash collisions happen, Python uses an algorithm called quadratic probation that tries to find a new index to place the index in the index table. Okay. Well, sorry. Let's talk briefly about sets. Let's say that they are very similar to dictionaries. They have an hash map, an hash table under, but they have a few differences. For example, they don't have values, they just have keys. Now, if you think about it, if you didn't know that before, this explains the magic of dictionary sets removing duplicates, because the same value passed to a hash function produces the same output. So you cannot have duplicates. Okay, in this case, the insertion order is not preserved because there's only one table. Yeah, this is a little example of how to use a set if you never did. They're called hash sets in the theory. Okay, let's do a little a fast comparison between the in operation performed on a list and on a set. Which one is faster? Of course, because you access the value directly. Okay, it's significantly faster. Even though, like, I measured also the creation of the data structures, so that does not make a difference. What can we learn from these? I guess the power of hash functions. You can use them for a lot of things, like, for example, to check the integrity of a file, and many other things, security and so on. Well, of course, lookups are way faster on dictionaries and sets than lists, because you access values directly in memory. Okay, so did we answer the fundamental question? First of all, let me say that I think it's really cool to dig deeper and learn low-level stuff, binary logic as well. But I think the answer is yes. This is me encouraging everyone to try and dig deeper and study a bit more how things work, because this way we can be better developers who write faster code and even greener code. A faster code is less energy expensed. So that's me with hair. I'm Salvatore. I work for Kraken. I'm a software engineer. I love Python and Rust. That's my website. If you want to check it, you don't miss anything. A few words about Kraken. Kraken is a software company that makes a platform for utility companies, especially energy. It's awesome. We're more than 1,500 developers. Remote first. Check us out. We have a stand. We have cute plushies. There's also a job position open for Italy at the moment. You can find it on the PyCon website. And that's me. Thank you.
Okay, thank you. Perfect talk and perfectly in time, so no problem. I have no question, no Slido, but we have 5 minutes for question. If someone in the room can post a question.
I know it could be like a bad question, but for tuples, have you tried to just, for curiosity, take a look into them, if they are weird beasts or...
Thank you for the question. Not much. I know a few things. Tuples are arrays in memory, and they are not mutable. So when you create them, you cannot modify them. If you try to do that, their memory position changes. And a fun fact is that they are hashable. I mean, you can perform a hash function on them only if their elements are hashable. Yeah, I don't know much more than that. I don't think there's any complicated things behind them.
Other question? Oui.
My recommendation is to use always tuples if possible. My recommendation is to use tuples always if possible instead of lists. Because the difference between the tuples and lists is that lists have a pointer which is always allocated and dynamically. Whereas if you take a look at the tuple structure, it's static. So basically, if you have a tuple of 3 elements, Python takes the basic structure from tuple and then also extend this structure by adding 3 positions for holding the 3 elements that you're getting inserted on the tuple, okay? And it's static. So it's just one single memory allocation that is done. Lists, no, we have 2 memory allocations. You have the memory allocation for the PyList, which is 1, and then we have the memory allocation to the list of elements, which is, of course, put on inside the first one that points to the concrete elements. So you have an indirection. It's also slow when you access element from a tuple and a list, because with the tuple you can immediately access the element that you want. With the list, you have to first access the pointer to the items, and then you have reference this to accessing the element that you want. So that's also the reason why it's best to always use tuple if possible.
Thank you for the presentation. What I was going to ask, something that we, I guess, remember after the presentation is try to use more carefully the append on list. So I guess the question for me is, if I don't know initially the size of the list, therefore the benefit of append is that I can dynamically append item there. So should I then go for an initial size and then resize as I would do in C, or shall I just forget the fact that maybe I will have some empty space at the end?
Yeah, thank you for the question. I wanted to mention that, but I forgot about it. And yeah, so if you do not know the size of your list priorly, there's not much that you can do about it. Python solves you the problem with the function that we saw, over-allocating. Yeah, so just forget about it, I think, and use append. It depends also on the performance that you need to achieve. If you use Python, I mean, usually you are not required to have huge performances in terms of speed. Good question. I do not know. It will be interesting to look that up. If you come to me later, we can look that up. Thank you.
Okay, thanks again, and that's all.